So today we're going to be discussing the idea behind pulses, but not like the human pulse. We're actually going to be discussing something a little bit more universal and something that once again is just a little bit unexpected. In this case, we're going to discuss a series of rhythms that seem to govern everything from the electric fields on the planet to the way that fireflies seem to flash in certain locations on the planet. And that's because for a very long time, biologists noticed that in a lot of cases, certain patterns in nature do not seem to be coincidental, and certain patterns seem to be the result of fundamental physics. And today we're going to take a look at one of such observations with the recent discovery suggesting that animal communication across the entire planet might be tuned to a very specific universal tempo, or a very specific frequency that most life on the planet seems to prefer. But to understand the implications and why this is not that unusual, let's first discuss a slightly different frequency that has been known and studied for a very long time. Let's discuss the Earth's background hum. And so here let's take a look at Earth itself. And since the 1950s, we've known about something referred to as the Schumann resonance. And to understand this, think of Earth and its ionosphere, or basically the layer of charged particles in the atmosphere, as a kind of a giant bell. And between the ground and the ionosphere, there's a hollow space that actually acts as a kind of a waveguide. And because our planet is filled with a lot of electromagnetic activity, and specifically thunderstorms, every time lightning strikes, and this happens 50 to sometimes 100 times every single second somewhere on the planet, this ends up releasing a burst of electromagnetic energy that then starts to bounce around inside the hollow space and encircling the globe. And since Earth has a very specific size, and the atmosphere is generally the same size as well, a lot of these waves then interfere with each other and actually create a kind of a permanent standing wave. And this surprisingly creates a constant hum that vibrates at a fundamental frequency of about 7.83 Hz, or roughly around 7.8 times per second. And so here it has a fundamental node and even second order and third order nodes, because this is literally a permanent standing wave. But this is not just some kind of a curiosity or something that's, I guess, fun to know, because this wave is sometimes actually used as a kind of a global thermometer. And that's because lightning generally increases with temperature, which then causes this Schumann resonance to also increase in strength, and then allows climatologists to track different changes, and specifically different weather patterns, across the entire planet without even going there, while also allowing us to estimate the total amount of lightning on the planet, indirectly tracking the amount of water vapor in the atmosphere, or, interestingly, it can also be used in geophysical surveys to help locate offshore hydrocarbon deposits, or basically it helps us find oil somewhere in the ground. But since other planets also have lightning, very similar effects have also been discovered there as well. For example, not so long ago, scientists discovered very similar patterns on Mars, and we know that Jupiter and Venus seem to have them too, but their versions are different. And so by studying these patterns and by detecting these types of frequencies, we can actually remotely sense what's happening on those planets by just detecting their own versions of Schumann resonance. But I guess the point of me starting with this is that our planet has its own natural cycles and its own natural frequencies that a lot of life very likely adapted to. But while Earth pulses at 7.8 Hz, a group of researchers recently discovered that a lot of living organisms seem to pulse at a slightly different and also very specific rhythm that's just a little bit different. And this actually started as field work in Thailand. And so here, Guy Amiche and his team were actually filming synchronous fireflies, or basically fireflies that tend to blink with the same pattern. And while studying these fireflies, they noticed something strange. The fireflies were flashing and nearby crickets were chirping with a somewhat similar pattern. And to the human ear and to human eye, they actually seemed perfectly in sync. Both fireflies and crickets were producing their own synchronized events. But importantly, when the team analyzed these discoveries, they actually realized that the animals were not actually listening to each other at all and were not even trying to communicate. Each of the species was doing its own thing, yet both species were pulsing at almost exactly the same rate of 2.4 Hz, or 2.4 times per second. once again, both crickets and fireflies were producing exactly the same frequency of pulsation. And so here we had our first mystery. Was this some kind of a wacky coincidence, or is there actually something going on here? And so they actually started to look for other animals and try to find similar modalities and similar frequencies there as well. And in this case, they sampled dozens of different species, from birds to frogs to fish, mammals, and even crustaceans. And the discovery in this case was kind of remarkable. Independent of the size of the body, so basically from really tiny things to enormous animals like whales, the tempo of communication signals seemed to cluster around a very narrow band of frequencies, between 0.5 to 4 Hz. And there was a very strong preference for one type of a tempo, 2 beats per second or 2 Hz. Here's actually roughly what this graph looks like. And it essentially shows us an overwhelming preference for approximately 2 Hz in frequency. And so here we had this very bizarre universal pattern. Why 2 Hz and what is this 2 Hz? Because a lot of animals seem to prefer this. And this didn't just involve flashes or chirps. Here things like, for example, frog calls, bird mating displays, or even vocalization and gesturing in mammals seem to always be around 2 Hz. As a matter of fact, here researchers jokingly refer to this as Taylor Swift constant. And that's because in humans this rhythm is also very prevalent in popular music. And most pop and rock songs, including most songs by Taylor Swift, usually cluster around 120 beats per minute or exactly 2 Hz. Which also surprisingly matches the walking speed of a typical human. And so, why 2 Hz and what makes it so special? I mean, based on what I talked about before, you would assume that this would be closer to 7.8 Hz, just like the Schumann resonance. But life seems to have chosen its own beat. And so what's with this unusual biological hotspot? Well, actually physically, there is no reason for this to exist. And that's because there's nothing stopping a frog from chirping 10 times a second, or for a firefly to flash much faster. But surprisingly, they don't. And in this case, researchers believe it's probably not because of how these noises or these flashes are made, but because of how receiver then interacts with them. In other words, it's all about who they're talking to and how the animal receiving these signals perceives them the best. Or basically how the animal listening or watching processes the information inside their brain. And so here, the potential explanation seems to hint on the biophysics inside neurons, because that's actually one of the few things that unites all of these animals. And so let's briefly discuss how neurons process information. And normally, a typical neuron requires a very specific amount of time to process a signal. Normally, after firing, they actually need just a little bit of time to refresh themselves before they can fire again. And for many different types of brain cells, this integration time is approximately half a second, which is usually the time window between the collection and summing of incoming signals and before the neuron is able to output its spike. And to try to test this hypothesis, the team behind the study essentially built a computer model that tried to recreate a neural circuit in order to see how this would respond to various rhythms. And using this model, they found that a lot of these circuits seem to be most responsive or seem to be most resonant when the signal was approximately 2 Hz. And so if the signal was too fast or too slow, the brain could not keep up and the information was not processed in the optimal way, or sometimes would not even grab the attention of this modeled computer brain. And so based on this, researchers now suggest that 2 Hz is a kind of a carrier frequency, or to be more exact, carrier frequency of life, at least life with a brain. And so just like the Earth's Schumann resonance, which is a byproduct of planets' geometry and its lightning, this 2 Hz frequency seems to be an animal pulse created as a byproduct of brain cells and neuronal interaction. And it seems to potentially serve as a baseline for a lot of different species to communicate most efficiently, because this is the rhythm most brains seem to be sensitive to, which would naturally explain why most of our music seems to usually have very similar beat. It's almost never faster or slower. And in some of the more recent studies, researchers even found that a lot of human language, independent of its location, seems to also follow this pattern. Across different cultures on different continents, the rate at which we produce intonation units, or basically the chunks of sound, seems to also have a very similar pitch. It's usually between 0.5 to 4 Hz, implying that even our speech seems to be tuned to the same pattern. And so there's no exact frequency that all animals prefer, but it just seems to be between 0.5 and 4 Hz. And connecting this to how neurons seem to process information right now makes the most sense. And surprisingly, this is once again very similar to fireflies, crickets, frogs, and pretty much most animals. But for all we know, maybe in some of the future studies, scientists might find some other explanations or possibly discover additional patterns that were actually missed in this study. Because by itself, this is a pretty important discovery, especially when it comes to trying to understand the origins of animal communication or even the origins of human language. Naturally, this also has certain implications for some of the astrobiological research, because assuming we do find life somewhere out there, their communication might also be governed by very similar physical limits and very similar environments or biology. And if they do have brains made out of cells that usually take time to reset, they might also pulse with very similar tempo. But when it comes to animal language, we're actually going to be discussing another really exciting discovery and something that's super mind-blowing from a separate research on cetaceans or whales. Because here we had some major breakthroughs in trying to actually understand what they're saying and trying to figure out how they talk to each other. And so if you would like to find out more, make sure to subscribe because that video is coming out really soon. But when it comes to understanding these types of patterns, right now we're still, I guess, in the early stages. Which means that we'll probably learn more in some of the future studies. For now though, next time you hear a Taylor Swift song, or possibly hear a chirping cricket, remember why they're doing this. This is basically one thing that seems to unite all of us. We have neurons that seem to work in a very similar way. And even our planet is vibrating in its own way, reminding us that we're just part of a much larger system. On that note, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining the channel membership that grants you early access. You can also support this channel by buying a Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.